Swayam Prabha. Digital India. Educated India.
So good morning everyone. So we covered two sections yesterday with respect to OpenACC. What I plan to do is to cover the third pragma that we have been talking about, which is more about optimization. There were a lot of questions who had already started working on the third lab. I will try to demystify or try to see and answer some of those questions during this presentation. And you can continue working on the third lab. And there have been a request with respect to showing the visual profiler rather than the command line profiler. So I would try to have a session. So this will be around 1 hour session where we will do hands-on. After that, I will show a live demo to you with respect to visual profiler on the Param system by CDAC. It requires X11 forwarding. So I will show you a demo. And then after that, we'll move on to the other sessions. So loop optimization. So what we are going to cover in this session is something called as how do you control this gang workers, what are these workers and vectors. You would have seen the minfo output. It would have printed out the vector size is this, the worker size is this. Then we will talk about the profiles, loop optimization, and then where to get help again, which is generally common for all the three sections. So let's look at them. So this is a very simplistic view. So let's make it as simple as possible. Suppose you had a house and you wanted to paint that house, right? So you will hire a worker. That worker basically does the work of painting the house. And since he's doing basically a sequential job and he's just one person, it takes a long time for him to actually paint that house, right? So now if you see over time, I don't know how many of you have seen somebody painting the house, but there is, so how much work can one worker do, right? A single worker can only move so fast. So if you would have seen the new kinds of the way people have been painting, they have a very specialized roller, which is much more wider, right? So if you just have a paint, which is just a painter is doing like this, he will have just one stripe. But nowadays, there are specific tools which are like these kinds of rollers, which can actually do a larger paint on your wall. Have you seen, anybody has seen such kind of a roller? If you have seen, you would understand that, right? So what we are doing is actually, instead of painting only one stripe, based on the width, based on the length of the roller, you can actually do much more in just one shot, right? So this way you can actually increase the productivity of one worker if he is doing that, right? What about we take more workers now and all of them start working in parallel? That will obviously make it better. But making all of them work is different from making all of them work in a coordinated fashion, right? Because they need to talk to each other. One worker cannot come to the other workers and start painting on his wall and stuff like that, right? So they need to coordinate among each other. So there is some kind of a coordination which is required, right? Just to give an example, so by organizing our workers into groups, we call them as gangs, right? So group of workers together make one particular gang, right? And this group of gang on different floors can operate independently, right? Because one floor painting is completely different from the ground floor painting, right? They can work independently and they do not talk to each other. While on the ground floor, these workers might have to talk to each other because he will say, okay, you paint this wall, I will paint that wall, right? So they need to coordinate. While this guy, ground floor guys, need not talk to the first floor guys. So the differentiation is people, gang, workers who are in the same gang at the same floor may have to coordinate with each other or talk to each other while they need not talk. So the bottom line is, there are a set of workers together form a gang. One gang is completely independent of the other gang, right? They cannot coordinate, they cannot synchronize, they cannot do anything. This is a restriction which has been put. People who belong to CUDA world who have already coded in CUDA, this is equivalent to the same thing. One block cannot talk to the other block, right? So since gang operate independently, we can have as many of them or as few of them, right? And if suppose we had only 2 gangs and we had 4 floors, 2 gangs are working on the ground floor and first floor. When they are done, they can jump to the second and third floor, right? Now think of it like this. If you had more, the first generation of GPUs had certain amount of SMs and we launched say 2 gangs. So suppose it has suppose it had 2 processors, then it will actually get scheduled there. When we increase the number of processors, since they cannot talk to each other, they did not synchronize with each other, it scales almost linearly. That's why CUDA programming model has proven to be really scalable. Whenever we release a new GPU, since these gangs are working independently of each other, or in CUDA world, since these blocks are working independent of each other, they can be scheduled anywhere, right? And the scheduler's job is very simple. So it can scale pretty much linearly, right? So to summarize the topic is that our painter was like a worker, right? He can only do some amount of work. By having a roller, you can think of it like a vector. Vector is nothing but in one shot you are actually doing not one element, but you can do multiple element in one shot. So if you would have seen the minfo output carefully yesterday, you would have seen the vector size as 128, right? So that 128 is basically, there are 128 operations being done in one shot by a group of, by a worker having a 128 vectors, right? So that's the concept. And then you can combine these workers together to make n number of gangs. So it's not so simple as you would traditionally do in any other programming model, like you just have threads and cores. There is a 2-level hierarchy here, right? You have vector, you have workers, and you have gangs. And you can control this basically by using certain construct which we are going to look at. And you are going to work on yesterday's code to optimize it to get the best number which gives you the best performance, right? So I think yesterday we have already done that with respect to how to add pragmas and loop and all. Now you can, there are other pragmas that you might look at. You have already, I heard that you have already looked at OpenMP collapse. I saw some of you already adding collapse clause. This is one of the most important, I would say, clause which exists. So why is it used? What does collapse do first of all? Is that it will collapse 2 loops into one. In this particular case, there is a I loop, there is a J loop. What it will do is when I say collapse, it will make only one loop and it will start from I equal to 0 to I is less than size star size. It will just collapse it to only one loop. Why would you do that? So think of it like this. Suppose your outer loop was only running for 32 iterations. Inner loop was running for 32 iterations. As I said, if you just make the outer loop parallel or just make the inner loop parallel, it will not have enough parallelism, right? So by collapsing, you will actually increase the parallelism, right? So it's very important to notice what is the size, how many elements you can actually run in parallel. If the size of one loop is smaller, you can use this collapse clause and increase the number of threads or gangs or vectors that you are going to launch, right? So when you are coding, you might have to play around with this variable, and if you have time in the weather code, you will have to see this, because you will have to notice that what is the size which exists, and based on that you are going to make a decision. Do I need to do collapse 2? Do I need to do collapse 3? Because it's a 3 nested loops and there are 4 nested loops as well in the code. So do I need to do only 2-level nesting? Do I need to do only 3-level collapsing? All those decisions is something which a programmer takes, and he can actually write those kinds of loops, right? It also helps in memory locality, obviously. So this is an example. If this was a 4x4, it basically, when I say collapse of 2, so it is going to actually make it like a one-dimensional array, right? So it will just collapse your 2-dimensional array into a one-dimensional array, and then it will be just one loop which will get executed, right? So this is what collapse does. Now, so again, this is just a summary of collapse clause. So loop might not have enough iterations. Then collapsing outer loop might give you more parallelism because it increase the number of gangs or vectors, and obviously it can also help you in data locality. We have not covered the optimization part, so I will keep it on to hold for one of the sessions that I am going to do later on. So if you use collapse, you might see an improvement, right? So right now the card that you are using for this hands-on session is not V100, it is K80, which is Kepler card, which is an older card. So you might see a different performance on that particular card, right? Based on what kind of a card and how many SMs it has, it will give you a different performance figure. This one is for Tesla V100 with collapse clause. Now let's look at another clause which is called as tile clause. So now this tile clause is kind of different in the sense that you can actually exploit something called as data locality. So if you remember the example that we gave last time, you remember the activity that we were doing? We were taking the top element, bottom element, left element and right element. What is this? This is 2D locality, correct? So you are accessing elements in 2 dimension. There are certain codes where you might even need 3 dimension locality. So let's look at 2D locality. How many elements you needed left and right? How many? 1 on left, 1 on right. You can apply the same technique where you can actually have in some codes like in convolutions and all, when you are applying filter, you might need left 2, right 2, top 2, bottom 2. As soon as you keep on increasing this, from a cache perspective and from a locality perspective, the point which was covered in the previous session, it will not be optimal, right? Because when the cache actually gets the data, it actually gets the neighboring elements, right? It doesn't get the top element or bottom element. In that particular case, your performance kind of decreases when you are accessing in this fashion. You are completely memory bound. You might access you are actually accessing in a CUDA world, it is called as non-coalesced access, which means you are not accessing adjacent elements, you are accessing left, right, top and bottom. Now top and bottom are not sequential, they are air. So the cache gets hit because it is not an optimal use. You will keep on getting that data back and forth between cache. Luckily, some of these platforms, like one platform is GPU, it does expose you 2D locality and 3D locality. A different memory is dedicated for that purpose, for exposing 2D and 3D locality. Now a compiler can actually, if you give tile, it may try to exploit that special memory which is good for expressing 2D and 3D locality. Now, to just give an example, people from the graphics world would understand this. Texture actually exposes 2D locality. There is a separate memory called a shared memory also, which can help in getting 2D locality much more better. So if you provide this tile clause, there are chances based on the hardware architecture where you are running it, that it will give you better performance. Okay? I am not saying it will always give you, it will be based on what is your tile size and what is basically the hardware which you are going to run on, right? Not every hardware will provide you 2D or 3D locality, or it might not reshuffle your data to get this kind of a better performance, right? So tile clause is good when you have this. If you are accessing left and 4 based on the number of accesses, convolution size and all, you will decide this size. So in this particular exercise, you are going to play with the different tile sizes and then figure out which one is the one which is giving you the best performance, right? So this is just an example. If I create a tile of 2 by 2 here, it will actually create like this structure, right? So it will expose it in the 2-dimensional space of 2 by 2, right? So this is how tile clause works. So what you will do in the yesterday's exercise in the third lab is basically you are going to try out different tile sizes, and you are going to see which tile size gives you the best performance. Okay, so this is just a snapshot of the code which is on a different hardware. This might not be true on the hardware that you are running, for which you have got hands-on. So if you can see, 32 by 32 is actually giving me better performance, around 10% improvement as compared to the other tile sizes which are mentioned there, 4 by 4, 4 by 8, 8 by 4. It is generally recommended to have it not very odd. So don't put it like 3 by 2 and 4 by 7 and all, those kinds of odd numbers are not recommended. Try to make it equal, like 16 by 8. It's a multiple of each other, 4 by 4, 4 by 8, right? So they are kind of multiple of each other. So only try that combinations. Don't try very random combinations. It will not help you. And one thing additionally that you have to try in your exercises, try putting more than 32 by 32. Try 64 by 64 and see what happens. Okay, this is the exercise. You have to tell me the answer what happens when you put 64 by 64. So as I said, when you use tile clause as compared to collapse, because we want to expose this 2D locality, it might give you better performance. On Tesla V100, it basically provides you around 13% performance gain. There is another clause which is very important, and this is what is required you for that add-on weather code that I am going to tell you. The first question to you is, do you think when you are making this loop parallel, should temp variable be shared across, like all of them should access the same temp variable, or everybody should have a private copy of the temp variable? Should all the threads have a private copy of the temp variable, or it should be shared? Basically, everybody should write to the same temp variable. Sorry? Why is it private? It's a temporary buffer, and if everybody just writes, so suppose thread 0 was writing, suppose if the value there was temp of 0 equal to I, and based on that I was doing some operation, right? Okay, so let's go ahead. So if suppose after this statement there was a statement like a variable, suppose there was a buffer called as A which was equal to the size, and I say A of I equal to temp of 0 plus temp of 1 plus temp of 2. Okay, so what is the value for I equal to 0? What will the value of A of I? It will be 0 plus 1 plus 2, 3, right? For I equal to 1, what it will be? 1 plus 2 plus 3, right? So whatever is the value, everybody is going to have a different answer, right? So everybody should have its own copy of temp variable. This is something that you would have learnt even in your OpenMP, private, and there was one more clause. Do you remember? First private as well. So the first private exists here as well. So you need to declare this variable as private, otherwise everybody will write to the same location, which will result into wrong answers. Okay, you don't want that to happen. And what is this condition called as in the parallel computing world? It's a data race condition, where everybody in parallel is writing to the same memory location. When you make things parallel, you need to make sure that there are no data races. If you have data races, and this has nothing to do with OpenACC, but it is more of a parallel computing topic, where you have to make sure that no two threads at the same time can write or read from the same variable. There are no data races. There are different kinds of data races: read after write, write after read, write over write. There are different kinds of data races which are possible. To solve that problem, if I make this private, everybody will have its own copy and they will not basically write to each other variable. Similarly, there is first private and private. What is the difference between first private and private? Private will not initialize your value to anything. It may be garbage. First private will initialize the value of temp to your host value in the GPU as well. That would be the difference between first private and private. Okay. Now coming back to gang, worker and vector, yesterday people were asking why cannot I just write collapse? If you write this loop separately, you can actually define things like the outer loop will be a gang, the inner loop can be a worker, the inside loop can be a vector. You actually have that control of which loop should be what, right? Generally you don't play around with worker, that's the bottom line. But you can actually play around with this and see which one gives you better performance as well. So just to give you a snapshot or hint, if this size was 32 in a GPU or in that range, I can make this as vector because that would be optimal size. and then the other loop can be gang only, so that you can have launched so many of them. So you can play around and define here. What does this mean? I am collapsing the loop, and everything, this one whole loop itself will have gang and vector, right? So you can do these kinds of optimization as well. There are different ways in which you can optimize. Another example, there is another very, very important clause which is required in many cases, is that you can actually say for a particular loop, please don't make it parallel, keep it sequential, right? And that is defined by SEQ clause. When will you define a particular loop as sequential? When it is dependent, when there is a dependency, you can explicitly state that don't over optimize and don't make this particular loop as parallel, keep it sequential. This is also you can add in case it is required. So only the outer two loops will be parallel and the inner one will run sequentially. Okay, it will not be made parallel, right? So we have already covered this part. So the bottom line is, all the values which I am saying, let us take an example here itself. This is an array, correct? Any array by default is not private, okay? It will be shared across. Like whatever you store in an array will be always shared. While anything which is a scalar value, what is a scalar value here? I is a scalar value, it's an individual element. It will be private by default, okay? All the scalar values are private by default. All the arrays are shared, right? So that's why, since temp was an array and we wanted to make it private, we had to explicitly add private here, right? And that is what is shown in this particular slide, the rules, right? So by default, the scalars are first private and when used in parallel region, and private when used in the kernel region, right? So now this is something which is specific to PGI. In a GCC world, it may be that it may consider it as just private, right? OpenACC states that it needs to be private. That's what it states. So here PGI defaults to first private when it's a parallel region, and when you use kernel, if you would have done the additional section in the first lab, it becomes private, right? So these are some of the basically notions that you can go through later on as well. I am going to share these slides with you. Based on C++ and all, there are additional ways in which you can interpret it, and you can adjust the number of workers and gangs and vector length, and this is what you are going to do actually in your session. You can say I want the vector length. By default, the vector length of PGI, even though you didn't give it, was 128. Try changing it to 32, try changing it to 64 and see what is the performance gain that you get, right? So you can control that by these additional clauses. Vector length will define the number of vectors within one particular worker. You can define the number of workers and you can define the number of gangs as well. Yesterday somebody was asking this question, should I play around with number of gangs and all? It's not recommended to play around with gangs. What I would say for now as a beginner is that you should try to play around with vector length only, okay? If you start playing around with number of workers and number of gangs, you should understand this concept in more detail for a particular hardware, is what my recommendation would be. So you can do it like this in your code. That you're going to do is you can say collapse 2 and then vector length. You can try 1024, try more than 1024, see what happens, try lesser than 1024 and see what happens, right? So as you can see, after adding vector close, actually the performance have decreased, it has not increased. So it may result into performance gain, it may not result into performance gain, right? But there is one more topic which I like to bring here, is that it's something called as return on investment, right? So if you see, earlier we were talking about 20x speed up, 10x speed up, 10 times faster and all. Now what are we talking about? 13% speed up, 50% speed up, 20% speed up. As you go to these cycles, which is in the end, optimization is basically a never-ending cycle. You will keep on doing it till the time you bash it to that. In the end, you will start writing assembly code also if you want to write to get the best performance, right? But you have to stop where you are okay that, okay, this is the performance I can live with, right? So you started with 2x, 3x, 10x speed up. Finally, when you reach the optimization, you are talking about 10% speed up, 5% speed up, 20% speed up, not more than that, right? So you can try these optimization techniques, but your return on investment will keep on going down, right? More time you will spend to get that performance, but your performance gain will be lesser and lesser as the time goes forward. So you have to stop where you are okay that, okay, this is a performance and I am happy with it, and let me stop that cycle of analyze, paralyze, optimize, analyze, paralyze, optimize. You have to stop that whenever you feel that I have got good performance and this is okay for me to do it, right? So as I said previously, it's a good idea to set the number of gangs, let the compiler decide. It is not a good idea to play with gangs. Let the compiler decide it. You can play around with vector length. That will give you better performance based on the hardware, but don't work with this. It is very rare to use a worker loop. You don't play around with workers generally. You will play around with vectors primarily, right? And yeah, so when possible, the vector loop should step through your arrays, obviously. Vector is the one which is more prominent. And gang should come from outer loops and vector from the inner. Don't do the opposite. Gangs are always higher level and vector are lower level. So your outer loop should be gang and the inner loop should be vector, not the opposite, right? So these are certain, I would say, rule of thumb that you should follow. And closing remark, yeah, some details I provided you with respect to gangs, workers and vectors. And collapse clause was covered, tile clause was covered. And we are also said that how you can play around with the sizes of vector, gangs and worker, right? And also provided you with some rule of thumbs which you should definitely follow to get the good performance. If you follow otherwise, you are bound mostly 90% that it will not give you good performance. So these are some best practice guide that you should have. Okay, any question? Did anybody already try these clauses? Did you get any good performance by adding these clauses yet? You tried collapse and did it improve the performance? It improved the performance by what percentage? Around 10%? Okay. Try tile clauses as well and see, ideally tile clause is the one which will give you the best performance. So without any further ado, launch the same lab which I gave yesterday, directly jump to lab 3, finish this as fast as possible. The next lab would be a hands-on which are demo that I will show you of profiler and guided analysis which will be very, very nice to see because it will tell you different steps in terms of how you can optimize by making use of tools and not just leaving it to the imagination. Okay. So I hope everybody has finished the lab. So as per the expectation, what was the best result that you got? Which was the best? Was it collapse? Was it tile? If it was tile, what was the size? Sorry? Collapse was the best. How much improvement did it give you? Around 1 second improvement. So from 4 seconds it reduced to 3 seconds. Any other results apart from collapse? Tile gave you 3.8. From 4 seconds something, it reduced to 3.8. What was the size of the tile? 32 by 4. Any other results? Sorry? 16 by 16 gave you good. So all of you are using the same software stack, all of you are using the same hardware. So how come the results are different? Sorry? WOPs? No, but all of you are running on the same hardware, all of you are running on the same software stack. everything is the same. So how can all of you get different results? Cache data? Yeah, for all of you the data is also the same, right? The cache is also the same. So all of you should ideally load the same cache and all the cache should give you the same behavior, right? Sorry? Communication overheads. I am asking her communication overhead, your communication overhead and your communication overhead is the same for an application, right? So if tile 32 by 4 is giving best result for him, it should give the best result for you as well. Collapse should not give you the best result. So why is this difference? Yeah, maybe you didn't try 32 by 4. So everybody has different results. The best thing is, as I told in the beginning, programmers should try to obviously try these things. At the same time, they should make use of tools, right? To justify on why these improvements are happening, why the improvements are not happening and all. So right now, this session is a very short demo. We have been talking about profiling for quite some time now. So I will show you a very short demo of how a code can actually change the behavior and reduce the performance, and how a tool like Profiler can help a developer in identifying why it is giving good performance, why is it not giving good performance, right? So this is a very short demo, and I am running it on my own machine at this point of time. So I will show you the code first. So if you look at the code, the name So if you look at this code, basically this is a code where I have a structure for doing some operations on the image. Forget about the name right now, the name does not represent what it does, but basically what it is doing is, basically I have a particular structure. This structure has certain elements like RGB, hue, saturation, max value, min value and some values, right? And then if you look at the code, in this particular code, I am trying to do some operations on that code and launching some number of blocks and threads. You don't need to worry about the syntax of CUDA. See, the same concept will apply in OpenACC as well. And I am trying to do some operation on this particular function, right, on the GPU. Now, most important thing for you to note is, how does my data structure look like, right? This is my data structure, and how am I allocating the data structure? Using malloc or CUDA malloc in this particular case. So I am creating that array, right? So we have been talking about Profiler for quite some time now. So I am going to show you, generally what happens is, in a cluster environment, you have been learning about cluster and all. Cluster, it's recommended not to have visualization on the cluster in the compute nodes, right? Because it requires X11 forwarding. I was trying to set up this X11 forwarding, and then whenever I used to click on that cluster, which was somewhere far, the output used to come after 1 minute. The refresh of the screen used to come 1 minute. So what I did was, basically this cluster right now I'm running on is actually in US. Instead of doing that X11 forwarding, I basically made use of this particular profiler, which comes, in your case it will be pgprof, you have been seeing pgprof, this one is nvprof, both of you will give almost the same thing. So I am saying nvprof, and I am adding one particular variable here called as analysis matrix. I will tell you what this particular analysis matrix does, and then I am storing the output of the profiling into a file, okay? You see, -o means output. So you are storing the output when I run this program, and the program that I am running is basically a.out, right? Once I run this program, it is going to basically generate a file which is called as you can see, I have already run it for you, it creates that particular file. Understood? Now on my system, I have already installed the profiler. So on my system, I have already installed the profiler, even though I don't have a GPU on the system. My laptop does not have a GPU, right? But it can basically install the tools which are required for you for doing things like remote profiling, remote debugging, and all those features are present. So you can actually use a laptop, only install these tools like profilers and debuggers, and then once I have run it, I have copied that .prof onto my laptop. Okay? So I have copied that .prof from the cluster to the laptop, and then I have just opened it inside that profiler, right? So I will just open it, start once more to show you that how it gets opened. So this is file, this is the profiler, this is a visual thing that you had seen in your code. So I am saying file, and then I say open, and then since the name of the file is, I can just say this one, and the name of the prof was what? acm.prof, correct? I will just open it, and this is the window that you had seen some time back. This is the dummy example, but in a real world this whole timeline view will be full. So what it is showing is from 0 second till the time it finished, which is 0.8 second, what was it doing? I had only one function which was running, but I am just showing you what was this function. If you can see, I can just expand it and also see that so what I am doing is basically expanding my timeline, if you see. So this is my function. So somebody was asking with respect to what are the number of threads, what are the functions, what was the grid size. So your block size is equivalent to your vector size and workers and all. If you can see, this is the number of gangs, 4096 that I have launched, each having 256 threads, which is equivalent to the workers and the vector length that was mentioned here, right? But this is something which will tell you finally what did you run it with. But what is more important for me is another view which I would like to show you, which is called as the guided analysis. Okay, so this particular tab here, this is called as guided analysis, right? So what you see here, if I bring my cursor, can you see it's written guided analysis? Guided, as the name itself says, it's going to guide you what is wrong in your application and how you can improve the performance of your application. So let's see, when I run this, it says examine GPU. As soon as I say examine GPU, I have already collected these metrics, by the way, via which flag? Analysis matrix. If I give that flag, already all that matrix which it requires for showing you this view is pre-calculated, right? So as soon as I click, it comes very fast. It is not running your application again. If you were not giving that analysis matrix, it will basically, when I click on it, it will again run your application. It will give you more information. Then again I click on something, it will keep on running. I didn't want to do that, so I just collected everything and just I am loading it here, right? So what it is telling is that I don't have very good compute utilization. Obviously it is not good because I am just running one kernel and all, but let's go deep. I am telling I want to individual kernels, as we call in CUDA world, or the individual pragmas that you had put, let us examine. As soon as I say that, obviously since I have only one function, it is telling I should concentrate on that function, right? If you had 5 functions, it will sort it out based on the priority, right? What is the priority? Which will give more priority? The one which takes more time. It will be the highest. So it is telling my highest priority right now is this kernel. If you had 5 functions, it will sort it out in that. Now again, I am telling, okay, let's go deeper into why it is doing this. So once I click on this, now it is actually telling me what the problem is. Okay. So if you look at this graph, what it is telling me is that my application, let me not show it to you. So when I ran this particular kernel, my compute utilization is this and my memory utilization is this. Okay? This particular kernel, when I run, it has the problem of compute, this much percentage was utilized and memory was utilized this much. So what kind of an application is this? Is it compute bound, memory bound, or latency bound? Louder. It is completely memory bound, right? No matter how many cores I throw at it, no matter how much parallelization I do at it, it is not going to help me because most of my time is actually spent in reading and writing memory. right? So let me go deeper on can I improve it or not. So when you are memory bound, you will improve memory. You will not improve compute side of it. You will not maybe play around with threads and all, while you will try to see how am I accessing the memory, right? So let me just click on it. So it is telling me rather than doing any of the compute analysis or latency analysis, you should do memory bandwidth analysis. So once I click on that, it will start giving me more information. Okay, it will start telling me some additional information, like this one is in red, right? What is this red? Let me see if I can make it. So what is this red? It is basically telling me that I have consumed almost all my memory bandwidth. So now this particular one, I have actually can get 788 gigabytes. I was telling that Volta has around 900 gigabytes and all. As you can see, I have already consumed 788 gigabytes per second of that particular memory. So your memory is one of the key problem, that I have to get more bandwidth of the memory, or I have to re-access and see how am I accessing the memory. Now that answer is also kind of shown and a lot of hints are given. There are more stats here. I don't want to go into those stats, but there is some hidden information here which will give you more status, right? So what it is telling you is, this is something, it is kind of explained here. In fact, you can actually click on it. If I had the source code here, it would have actually given me both the source code view as well as the assembly level view of the code. So right now I don't have source code on my machine, so it is not showing me. But if you are really enthusiastic and if you are a ninja programmer, you can actually go till the assembly level itself of where your time is being spent. But let us not go there. I could have clicked there and gone there. But it is telling you many problems. It is telling you that you are not accessing your memory. There is an alignment problem in your memory. Okay? And you are not accessing your memory properly. So what it is also telling you is that whenever I try to load the memory, ideally I should load the memory in 4 transactions per access, but you are taking almost 32 to load this memory. 32 times you are the one who, for every memory access, you keep on loading it again and again. Now this is something which goes into the ninja side of it, where you need to understand what it is. I will try to make it simplify for you. Right now I showed you a data structure which had this problem. Now let me show you another code which uses another data structure but does the same operation. Okay? Now if you see this data structure, what is the difference between the previous data structure and this data structure? So this one does not have int r, int g or int b, correct? It has int star r. So I am allocating r separately, b separately, g separately, u separately, correct? So I will bring back the old code for you so that you get a feeling of what I am saying. Look back at your previous code again. This is how the structure was, R, G, B, hue, saturation, and I was creating an array of this structure, right? Right now I have changed that structure. I am doing the same operation, but I have just changed my data layout. So in the previous one, your data layout, if you see, was something like this. You had R, G, B, then hue, then whatever values was there, then again R, G, B, correct? Now my data structure is R, then G, 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 like this. It's a change in data structure basically, how you have stored the values, correct? So as soon as I now compile this code, run it, I have already created a profile for this, which is .prof here with the same command which I had told you previously. So if you just see, I have just run the same thing and I have created a acmsol.prof of this file. I have copied it onto my laptop again, and let me now open that file. Okay, before going there, let us first of all look at how much time this particular guy takes. Okay, so the properties, how much time does this kernel take? It's written here. Are you able to see it? So it started at this time, ended at this time. The kernel time, this running of this on the GPU takes 105 microseconds. Okay, 105 microseconds. Now let's look at the new timeline. In the new timeline, how much time it takes? 47 microseconds. So how much speed up did I get? Almost twice the speed up. Now I didn't even change anything. I have to change my data structure. I am doing the same computation. I am not changing the size of my threads. I am not doing anything. I just changed my data structure. Now let's see what does this guy tell again, right? So let me examine the GPU usage. Then again examine. Now this guy is again saying perform kernel analysis. Now again if you see, it is still completely memory bound, but it has reduced my overall time, and it is still telling that it is memory bandwidth bound, but my time has reduced, but it is not telling me what was there previously. Do you remember what was told previously? There is alignment problem, right? So I had to change the way my memory was aligned so that my accesses to the cache were better. As soon as I changed that, and now I went to this one, it has changed. It is still memory bound, but my alignment problem is gone. Now it will start telling something else. Now it will start telling that your throughput is good, this is good, but maybe you should try using another memory and all, right? So this has also come to 740 gigabytes per second. It has slightly gone down actually because the better. So this is what is called as guided analysis, right? In your kernel also, when you were trying to say, when I launch this, when I launch that, you can actually go to this, you can look at the properties view. When you click on it, you can actually go to the properties view and you can see what was the thread that were launched and all, and you can view it, why it was giving that problem and why this one is better as compared to the other one, right? And I would suggest that whoever is working in this field of parallel computing, they should always make use of tools rather than just guessing something based on. So what is this tool is, think of it like this, all the ninja programmers have come together and they have created this tool to guide the guys who are trying it for the first time, to guide them with respect to this metrics, that okay, you should focus here, after this you should focus here, after that you should focus here, this is the problem, that is the problem. If compute is not your problem, you will never play around with the threads and all those things and all, right? You will play around with the memory side of it. Understood? So this is what is the recommended way to use in a cluster environment especially. The main thing that we are talking about here is high performance computing. In a cluster environment, you don't run the visual profiler just like that. You don't do X11 forwarding and use it, because if you see in a cluster environment, you will have few head nodes, many compute nodes. All this X11 forwarding will go via the head node, and your head node will just go down because there are only few head nodes. It's only meant for doing compilation and stuff. You should not overload the head node with all these kinds of visualization softwares, right? So you should install these profilers, toolkits and all on your laptop. It doesn't matter whether you have a GPU or not. The only thing you have to say is no to the driver. Driver is the one which requires GPU. Rest all does not require. And then you can do remote profiling. In fact, the visual profiler is something which is old. We have come out with a new tool which is much more sophisticated, which is called as Insight System. The same UI that you are seeing, you will be able to see it in Insight System and compute. Same stuff, right? And this is the future on how people are going to basically see. So Insight System gives you a particular view, whole view of your system. Insight Compute gives you more detail about your individual kernels, right? Any questions on this? Everything is free. CPU profiling is also there. So when you are running your code, you can say -- CPU profiling on. So it will profile the CPU code as well. Insight System has more stats. Visual Profiler is kind of limited. So if you want to see your whole system view on what's running, are you doing OS calls like file operations and stuff like that, all that will be shown in a system profile view. It also shows you MPI calls, only synchronous MPI calls. Asynchronous is not possible to do in currently, But if you are doing MPI send receives, it will show, not async sends and async receives. Any more questions? No more questions? Is it clear? You can ask any questions related to the previous sessions as well, if you want.
What about asynchronous open ACC calls?
Yeah, so asynchronous open ACC calls will also be shown because it is taking the stats from the GPU. So whenever it executes, it will be able to show it. Whenever it started so it will show you a view where when it was called and when it got executed. That view will be shown.
Any reason why OpenMP asynchronous calls will not?
OpenMP. OpenMP doesn't run on GPU yet. Sorry? Yeah, because that is something for which you need to know the network stack. We need to poll the network stack on when it has started transferring the data and all those things. So currently it is not there. You may see it in the future. Currently it is not there. That support is not there. No, so you need to generate this profiling via the profiler, then only it can understand it. It cannot, so there are other profilers as well which all support GPUs. I am just showing you one profiler. If you have heard of Vampire, HPC Toolkit, all of them support ARM's profiler and tracing tool, all of them support GPU profiling. So you can even use those other profilers for profiling on the GPUs. This is a profiler by NVIDIA. So the reason why it is possible is because NVIDIA has created the API for profiling open. So anybody can use that API and create their own profiling and tracing tools. And that's how the ecosystem has got developed, that almost all the profiling tools, so like Vampire, Tau, and all of them support profiling on the GPU.
Can you also get some information regarding power consumption from this profile?
No. So you cannot get power consumption, but there we have another API which is called as NVML. So if you want, you can make use of those APIs, create your own tool and get that consumption pattern. But it will never give you a consumption pattern at a core level. You cannot do that in GPUs because if you see, GPU is a massively parallel architecture. It's based on that hiding latency principle. So you cannot trace at a core level or something. You will be able to do it at the GPU level.
Total power consumption of a GPU while running?
Yes, that is possible using this API called as NVML. So it's NVIDIA Management Library. So you can call those APIs and get those information. So the question is that why should we not run it in a cluster environment, right? So if you would have seen in a cluster environment, you will have one or two head nodes, and then you will have many compute nodes where actual computation happens. So first you will log in into head node. From head node, you will get access to the compute node. Now, if you want to visualize it, right, where will you do this forwarding? So generally in a HPC environment, you usually don't do visualization. What you do is you do compute and you can do rendering. So the output finally should be visualized on a remote system. It is not recommended to do this visualization on the compute cluster, and that's why it's called as compute cluster, not a visualization cluster. So you have to set up in a HPC environment, there are separate nodes which are meant for doing only visualization, because visualization will just take away, it's a very heavy task, and if there are only few GPUs and it's a shared system, all of them trying to access your head node will just go down, right? And then nobody will be even to even access that cluster anymore because your head node has gone down. There are very few head nodes which are there, right? So in case you have very heavy requirements with respect to visualization softwares, you should have separate nodes dedicated for visualization, which are called as visualization nodes. These are compute nodes, then there are head nodes, and there are visualization nodes meant for only doing visualization. You can transfer from the compute node to the visualization node, but in a HPC environment, generally you have a shared storage, like a network file system. So it is available on all the nodes. So you can later on go to the visualization node and view it from there. So it's all shared file system. So you don't get bottleneck of transferring. Right now I just showed you a view where I wanted to see it remotely on my laptop. So I had to transfer it. Sorry? Okay. Okay. So instead of just parallelizing that part, you also parallelize the initialize loop, and it gave you better performance. So you reduce the time further. So it's an optimization cycle, right? So bottleneck will always shift from one place to the other. Once you solve one problem, as per Amdahl's law, once you have reduced that 50%, the time shifts to the other 50%. Once you solve that, some part of it, it will shift to another 50%. You can keep on doing it. With initialize, you have reduced it further. After that, if it is possible, you can see further as well. So, yeah, so nice observation there.
After initialization, we started like before it's that it started. So it should not affect it actually.
So I have to see it myself. So this is a so my point is not with respect to initialization, but the point is that if initialization becomes your problem later on, so if you see most of your algorithms are iterative in nature, so initialization is a one-time activity. So mostly people generally don't worry about initialization because it will be down bottom in your hierarchy, but if it becomes important at that time, you can go ahead and initialize and make it parallel. No more questions?